Hello and welcome back. In this lecture, we will be beginning our discussions of Chapter 14. Chapter 14 deals with heat energy. Heat, or heat energy, gets the symbol Q. So heat energy is energy that is transferred due to a temperature difference. Heat flows from higher temperature objects to cooler temperature objects, and not the opposite direction. There are three mechanisms for heat transfer. Conduction, convection, and radiation are the three ways that heat can flow. So the first, conduction, is the transfer of heat from adjacent molecule to the next molecule, etc. So an example of this is if you take a metal rod and you hold one end and you put the other end over a flame. The end over the flame will begin to heat due to the fact that it is directly above the flame. The molecules directly above the flame that are within the rod will start to experience larger and larger amplitude oscillations because of the energy that is being transferred to them by the flame. Those larger and larger amplitude oscillations will cause them to push energy to the next molecule. That next molecule next to them with the gained energy will experience larger and larger amplitude oscillations, allowing it to push energy to the next molecule, its neighbor. The neighbor then experiences larger and larger amplitude oscillations, pushes to the next neighbor, etc., until at my hand I begin to feel the rod heat. So this is the transfer of heat energy via conduction. Conduction, the energy is passed from molecule to molecule to molecule, conducting along a medium. The second mechanism for heat transfer is convection. A place to see convection is in the atmosphere and also in the oceans. The atmosphere, one specific place you can see it is, for example, here in Albuquerque, gets very, very, very hot during the day in the summers. So when heat coming from the sun in the form of radiation, which we will talk about in a moment, coming in from the atmosphere, the photons stream down and they hit the ground. The ground then absorbs the heat energy from those photons and re-radiates. When it does that, the air that is just above the ground begins to heat. And as that air above the ground heats up, its density decreases, and so it rises above the higher density molecules that are cooler. So those cooler molecules now fall in next to the ground. The ground, again, hot because it is absorbing radiation from the sun, and as that air above the ground heats, the density decreases and it rises up, and now more dense, cooler air falls in. And so this is convection. This is the large mass of molecules that are moving due to density changes. It's keeping the atmosphere stirred up, also keeping the ocean stirred up. Radiation is the last mechanism for heat transfer, and this radiation has to do with the electromagnetic spectrum, fundamental unit being the photon. So the electromagnetic spectrum is enormous, and it encompasses a lot of different areas called radio waves, microwaves, ultraviolet radiation, infrared radiation, visible radiation, gamma radiation, X-ray radiation. We see one part of that electromagnetic spectrum with these detectors that are built into our head called our eyeballs. And that part of the spectrum that we can see is called the visible part of the spectrum. We also call it light. Photons carry energy. They're little packets of energy. And so radiation makes up the third mechanism for heat transfer. We can quantify two of these three, conduction and radiation. Convection is very hard to quantify. It needs to be approximated using computer programs, and we will not be dealing with it at this level. But we can quantify heat transfer via conduction and heat transfer via radiation. So the rate of heat transfer via conduction, rate being the heat per unit time that is conducted from one object to another, is drawn here on this picture. So I have a an object or a medium at temperature T1 and another medium or object at temperature T2, and they're separated by a conductive medium that has a thickness D and is dotted here to show that this is the medium. And the surface area is area A. So the rate at which heat is transferred from T1 to T2, I'm assuming that T1 is at a higher temperature. The rate at which heat is being transferred from T1 to T2 is equal to the thermal conductivity K. This is not the same K as we were using in chapter 13. K is a new quantity called thermal conductivity now, and it's how good of a conductor this particular medium is. And it's going to be dependent on what this medium is made up of. All materials have different thermal conductivities. They're measured empirically in labs and reported on a table that you would look up. So thermal conductivity of the material times the area between the area of the conductive medium times the difference in temperature. So this is going to be the temperature T1 minus T2 divided by the thickness of the conductive medium. So this allows us to quantify the rate of heat loss. Notice that if this is my home and this is inside of my home, this is the material inside of my wall, and T2 is the outside of my home. And let's say that the temperatures are exactly the same, so this is like a spring or fall day when the inside and outside temperature of my home is exactly the same, then you can see there's not going to be any heat transfer because T1 and T2 would be the same. If instead this is a hot day, then the outside of my home is going to be hotter than the inside of my home, and heat would flow into my home. If instead it is a cold winter day, then the inside of my home is going to be warmer than the outside of my home, and the picture that we're showing for the direction of heat loss would be exactly as is directed to the right. Inside would be warmer, outside would be cooler, and I would be losing heat through my wall. We want a conductive medium that has a very low thermal conductivity. When we talk about our home, we want this material to have a very low K value, a low thermal conductivity. So this formula allows us to quantify the rate at which heat is lost via conduction. The rate at which heat is transferred via radiation is described by this formula right here. So this is the rate of heat flow via radiation, and this is equal to sigma. Sigma is Stefan Boltzmann's constant. Stefan Boltzmann's constant is 5.67 times 10 to the minus 8 joules per second per meter squared per Kelvin to the fourth power, times little e. Little e is known as emissivity. Emissivity is a unitless quantity. It has values that lie between 0 and 1, and it's a measure of how good an emitter the object is. So when we talk about the sun, little e would have a value of about 1, and when we talk about an object that is an extremely poor emitter of radiation, then it's going to have a value lying closer to 0, times the surface area of the emitter, times the quantity, the temperature of the emitter to the fourth power, minus the temperature of the environment that is surrounding the emitter to the fourth power. These temperatures need to be in units of Kelvin, and you can see that by the units for Stefan Boltzmann's constant. You have Kelvin to the fourth power in the denominator. Rate of heat flow is going to be joules per second, so we're going to need to cancel that Kelvin to the fourth power that is in Stefan Boltzmann's constant. So these temperatures need to be in units of Kelvin. So, for example, you can see I've drawn the sun here, and we're losing heat. The sun is emitting heat per unit time. The sun has a certain temperature, and if you look up the surface temperature of the sun, it's about 6,000 Kelvin. and then it's surrounded by an environment which is space, and the temperature in the environment is about 4 Kelvin. So if we apply this formula to the rate of heat transfer from the sun to outer space, then we would have the temperature of the emitter being the temperature of the sun, 6,000 Kelvin, raise that to the 4th power minus the temperature of the environment being space, that would be 4 Kelvin raised to the 4th power. We can see that when we talk about emitters in space, the environment's temperature doesn't really factor in much at all, and we can pretty much ignore it. But if instead we talk about, for example, my coffee cup sitting in a room, the temperature of the coffee cup and the temperature of the room are not significantly different, and so the temperature in the environment becomes very important. So this is the general formula we can apply to any situation in which heat is being transferred via radiation. So this gives us an introduction to heat, the mechanisms for heat transfer, and the two that we can actually quantify as we move through chapter 14. And we will do that next time. Thank you.